So, after the wrapper has been designed, the next thing that we need to do for SOC testing is designing the test access mechanism. So, test access mechanism means from the system on chip pin, some pins will be dedicated for supplying the test patterns from the automatic test equipment to the SOC, and from those pins we need to transfer the test patterns to the respective code that we want to test. Now, as we know that it is if there are large number of codes, so it is not possible to have dedicated lines for each of these codes. So, many of these codes are to be put onto the same set of test pins. Okay. So, and also there is a question of doing an allocation, like maybe after consulting with the designer, it is found that we can accommodate say 60 such pins or 60 such inputs for the test bus design part. But out of these 60, so if we say that all 60s will be dedicated for testing one core, so that may be an inefficient mechanism. So, we may need to find out a partitioning of those 60 lines, so that it is divided into say a number of subsets, and each subset is dedicated to testing a subset of cores that are there in the system. And apart from cores, so we can also test the user defined logic UDL and the interconnections. Okay. So, as we have seen in different testing mode in the wrappers, so in test, X test, etc. Now, about the test access mechanism, so several types of test access mechanisms have been proposed in the literature. So, first one is multiplexed access. So, in a multiplexed access, this test bus is coming, and it is divided into 3 courses, C1, C2 and C3. So, the test pattern which is meant for C1, so there may be some device ID register with this C1, C2, C3 that will identify whether the test pattern is for C1 or for C2 or for C3. In the worst case, the same test pattern will be distributed to all the cores. So, that way that may or may not be beneficial for some cores, but it is so somehow the pattern is transferred to the core. And at the output, so there is a multiplexer. So, these responses from these cores are collected, and it is passed through a multiplexer that combines them onto the bus. So, this is so this TAM is consisting of this line which is coming from coming to the system chip from the ATE, and the lines which is going out of the system chip to the ATE. Now, in between we have got this multiplexed access. So, at one point of time only one core is being tested. So, the basic problem with this type of structure is that it will require large amount of time, since this testing is totally serial. So, we need to consider them serially one after the other, all the cores. So, it will take long time, but at the same time it will have the flexibility of having the minimum power consumption, because at any point of time only one core is being tested. So, the power consumed by that core will only come into picture. So, if one core consumes, the maximum power consumed by any core is say P, then the maximum power consumption is given by P. However, the maximum power consumption of the entire test session is given by P. However, it can since the test is prolonged over a long time, so this test time is maybe quite high, and that will cause the testing cost to go high as well. Second approach is daisy chained approach. So, where we have got this the test bus is running, and from the test bus this input is going to the core, and it is passed to either the response will be passed or the test bus will be passed. So, this response, if the response is passed, then in the remaining part of the bus, so it will carry this response through the bus. So, here also at one point of time only one core is being tested, but instead of having a one multiplexer here, so we have got multiplexers at the end of individual core, just to select the response, which response to be carried out. So, this is some sort of daisy chained structure, because if C1 is not using the test bus, then only the test bus will be available for C2. If C1 and C2 both are not using the test bus, then the test bus will be available for C3. So, this is known as the daisy chained approach. Another possibility is the distribution. So, the point I was talking of at the beginning is that in the first two cases the entire test bus is getting allocated to testing of a particular core, but that may not be very beneficial because that makes the testing fully serial. So, if we can distribute this test bus into a number of sub buses, like here we have got we have divided the test bus into 3 parallel buses, sub buses, and they are actually feeding the individual cores. So, the point is that here I can think of some parallel testing, like a this C1, C2, C3, they can be tested in a serial fashion, they can be tested in a parallel fashion as well. Maybe C1, C2 are tested parallelly, C3 tested separately, or all C1, C2, C3 are tested parallelly. So, it depends, like but of course, again the test bus is getting distributed, it is getting divided into the three parts. So, the width of individual test buses are going to be small. So, from the wrapper design example we have seen that if we allocate lesser number of lines for parallel access lines, lesser number of WPI lines to individual cores, then the test time of that core will also be high. So, that is there, but still we have to decide on how this partitioning can be done, but if the partitioning is followed, then we can go for parallel testing. Of course, we need to take care of the power consumption that is there in that will come if a number of cores are tested in parallel. So, there are several approaches like multiplexed access, then there is reuse system bus, then there is transparent paths, isolation rings, test bus, test rail, etc., which are actually some combination of these philosophies. Okay, so, we will look into them in the successive analysis. First of all, the test bus architecture. So, in the test bus architecture, so this SOC, so these are actually the test lines that are running. So, here the width of the original bus is 3 plus 4 plus 2, that is 9, and that 9 width bus is divided into 3 sub buses, you can say. So, I can say there are 3 buses as if there are 3 buses, one bus is of width 3, another of width 4, another of width 2. Now, this core A and core B, so they are put onto the bus number 1 having 3 W equal to 3, bus width equal to 3. C, D and E, they are put on bus number 2 having width 4, and the core F is on bus number 3 of width 2. Now, so this A and B, they cannot be tested parallelly because they are on the same bus. Similarly, C, D, E cannot be tested parallelly because they are on the same bus, but I can parallelly test A and C, I can parallelly test A, C and F, provided other constraints are met, like the power constraint, precedence constraints, so those are met. So, we can go for parallel testing of all the 3 or this the cores on the 3 parallel buses. So, it is a combination of multiplexing and distribution. So, we are distributing the original TAM width W of 9 into 3 buses, so of width 3, 4 and 2. So, that is the distribution, and it is a multiplexing as well, because at one point of time only one core on a bus will be able to use that bus. So, it is a multiplexing. So, it supports only serial schedule. So, serial schedule means one after the other they are to be tested. So, A and B on the same bus, they can be tested serially only. Core external testing is cumbersome or impossible. Core external testing means you have to somehow put these interconnects onto say suppose I want to test an interconnect from A to E, then what is required is that on the A bus I have to put the value that we want to pass through the interconnect at the output, and then that output has to be sent to E, and again I have to sense it here. So, this is difficult because it is not happening on the same bus. Okay. So, 2 different buses are getting involved when we are trying to test this interconnect. So, that makes the external testing part a bit difficult. So, maybe impossible also in some cases if we do not have this type of buses available. So, a typical serial schedule will look like this, that A and B, so they are tested one after the other in this in the TAM and in the first TAM. Similarly, C, D and E, they are tested serially on second TAM, and F is occupying the third TAM, and the total test time is given by the maximum of test times of individual TAMs. So, that is basically given by the TAM 2 in this example. Then we look into test rail architecture. So, test rail architecture, it is a combination of daisy chain and distribution. So, previous one was a combination of multiplexing and distribution. So, this is a combination of daisy chain and distribution architectures. So, codes connected to a test rail can be tested simultaneously as well as sequentially. So, what is happening is that the test pattern that is going through this going into this rail on this rail. So, they can be, so in the initially these multiplexers, they can be programmed so that this test pattern reaches all the codes. So, if it is possible that all the codes they are going to have the same test pattern, then the same test pattern can be fed, or it can be that first these test patterns are shifted serially for all the 3 codes, and then they are applied to the code, and then when the responses come, then responses are also serially shifted out. So, that can be done. So, that is why it is a combination of so it can be tested simultaneously. The C1, C2, C3 can be tested simultaneously as well as sequentially. Sequentially we can always do. So, we can do it sequentially. So, here actually this with the, so if it is so in multiple wrappers can be activated simultaneously for X test, because I can have this wrapper of C1 and this wrapper of C2. So, there may be some connection between C1 and C2. So, for X test, so I can send the test pattern here and I can get the responses from this point. So, that way I can simultaneously do this X test operation. And now, this test rail can be of fixed width or it can be of flexible width. The first example, this is a case of fixed width test rail. So, I have divided the total rail width W into 2 rails, W1 and W2. So, W1 on W1 we have got C1, C2, C3, and W2 actually these 2 should be C4, C5. So, this is wrong. So, not C1, C2, C4, C5. So, this on W2 we have got C4, C5. That way the code distribution is done over the rails. On the other hand, in this case, the second example, the width is not fixed. Okay. So, initially the total W comes here, out of that some part of it may be fed here. Maybe for C1 we have taken say W1 W equal to say 5. So, 5 bits will be used as for transferring test pattern to C1, and the remaining bits are coming here. Okay. So, now so that similarly for C2, so we may have, say we may require 10 bits in the wrapper. Okay. So, the WPI lines for C2 may be 10. So, as a result we have got say 10 lines going from this W into C2. So, that actually gives the scope for parallel testing further, because if the distribution is such that say the first 5 lines are connected to this C1, second 5 lines are connected to this, third 5 lines are connected to this, then I can send 15 bit pattern and that can feed this C1, C2, C3 parallelly. So, that can be done. That is another way of getting parallelism with flexible with rails. And of course, in this case what is happening is that maybe the preferred width preferred tam width for C1 is not same as the preferred tam width of C2, but we do not have any choice. Once we have the made the distribution into W1 and W2, we have to test them with this fixed width only. So, the test time is going to increase compared to their best possible time. Whereas, in the second case, since it is flexible, so we have got the choice. So, we can, as long as the total tam width requirement does not exceed W, we can distribute this tam width into different codes differently. So, so there is no distinct test rail onto which the codes are placed. So, so that becomes a gives the flexibility to the overall scheme. So, there are a number of problems that have been formulated for this wrapper tam co-optimization problem. So, what is happening is that, so this wrapper optimization and the wrapper selection, wrapper design and this tam design. So, they are going to be 2 problems which are dependent on each other. Like for every core, we have seen that giving different tam width in the wrapper, giving different WPI lines in the wrapper. So, it generates different test time for the cores. Now, at the same time, when I am having a tam given to me, I need to partition them, for example, and this partitioning should be such that it is doing the best one for all the cores ideally, but that is not possible. So, we have to have some trade off. Okay. So, we have to find out a good tam distribution, so that these cores are getting the tam lines which are so that their wrappers will not require prohibitively high amount of test time in the after the wrapper design. At the same time, the tam width should not be so high for a few cores, so that for other cores we do not have enough tam width left. So, this is actually the problem. So, we have to look into this wrapper design and this tam partitioning together. Okay. So, there are some works in this direction. The first one in that direction is the known as the problem PW, which is actually the wrapper design. So, here only the wrapper design problem is solved. So, for a particular core we find out what are the different wrapper configurations that can give very good results. Then the next problem is known as PAW. So, that is core assignment plus PW. So, plus wrapper design. So, in the PAW problem, it is assumed that the tam partitioning has already been done. So, that is like this W, it is told that it is divided into 3 tams of width W1, W2 and W3, and now the problem is to do core assignment, like which core should be placed on which tam. Okay. And then, for example, in this case you see the first IP it has been put on W1, second IP has been put on W2, third one as on W3. So, if there are more number of IPs, so they will be sharing this W1, W2, W3 buses. Okay. They will be sharing them, but how to decide like what is an optimal distribution of the cores to the this buses. Okay. And of course, so we have to this distribution of this cores to the tams. Now, of course, we have the issue like if we have different width given to different cores, then they will take different amount of time. So, overall objective is to minimize test time, but this PAW problem, so it solves this wrapper design problem plus core assignment problem together in an integrated fashion. So, it is expected to have better result than this PW based problem formulation. Then the third problem formulation is known as the tam width partitioning plus core assignment plus wrapper design. So, here it is told that okay, total width is W and I want to distribute it into 3 or 4 or 10 number of tams. Okay. So, but how do you do the distribution? So, that is not told. Okay. So, a solution to the problem will suggest me the distribution of individual of this tam widths to different tams, and second thing is that it will do this core assignment and it will also do the wrapper design. So, it will do 3 things together. Okay. So, tam width partitioning plus core assignment plus wrapper design. So, that is known as PAW. Then there is another version of the problem which is known as PNPAW. So, where this number of tams is also not told. So, it is asked that you come up with a proper number of tams, then do the partitioning, then do the core assignment and also the wrapper design. So, this PNPAW is the most generic version of the problem when we are talking about this partitioned tam based approach. Okay, but naturally this PNPAW is the most difficult problem to solve. So, there are many formulations that have been reported in the literature. Some of them are based on integer linear programming, some of them are based on heuristics, some of them are based on meta search techniques. So, these have been reported. Okay. So, in the literature you can find out, but this the PNPW is the most generic one. So, normally there are lots of works solving the PAW problem, and there are some works based on PNPAW problem. So, we will see how can we formulate it as a mathematical problem. Okay. So, if we so it can be formulated as an integer linear programming type of problem. So, for that we have got some decision variables xij. So, xij, this decision variable is equal to 1 if core I is assigned to tam j. So, if I have got say n number of cores and m number of tams, then there will be this xij variables, it will be n into m number of xij variables will be there. Now, every term. So, if we once I say that it is assigned to term j, so it is assumed that term j's width is known. So, it is basically a formulation for that PAW problem, where the term widths are known, the core assignment is not done. So, this width the width is known. So, here this will be assigned. So, this xij equal to 1 means that core I is assigned to term j. Testing time of core I on term width of j, which is given by wj, is tiwj. So, this value we can find out from the wrapper design procedure. So, we can do a best possible wrapper design with the available number of term lines, and then we can compute what is the time needed for transferring the test patterns to that core based on this particular term width, and compute what is the total time needed. So, test time on term j. So, test time on term j is given by this sigma of this tiwj multiplied by xij. So, if xij equal to 1, that means the core I is being tested on term j. In that case, this tiwj factor will get added. If xij is equal to 0, that means this core is not tested on this term. So, it does not contribute to the testing time of term j. So, this computes the testing time of term j, and the objective is to minimize this maximum value. So, this maximum over all terms of this test time values. So, that gives the total test time for the system, like in this example that we have talked about. So, here you see that for this term the test time is given by that this plus this. So, these two time summation. Similarly, this term it is test times of CDE. So, we take the maximum of these three. So, this gives me the maximum time. So, in the objective function we would like to minimize that maximum value. So, that is what is written here. So, we want to minimize the total time t, which is given by maximum of all these individual term testing times. Now, there must be some constraints that has to be satisfied by, like say sigma I xij equal to 1. So, every core must be assigned to only one term. So, for one particular core, say core I xi 1 is equal to 1 if it is assigned to term 1, otherwise it is 0. Similarly, xi 2 is equal to 1 if it is assigned to term 2 and it is 0 otherwise, like that. So, this sigma I xij, so this actually gives us the thing that this the sum of all those xij variables, and this equal to 1 signifies that only one of those xij's is equal to 1, and that means the core I has been assigned to exactly one term. Okay. So, that is the first constraint. Second constraint that we have is that the width of all these terms. So, this partitioning that has been done. So, sigma iwj equal to w. So, for all the terms, so this should be sigma on j, this is sigma on j wj should be equal to w, the total term width, and finally any term width wj must be less or equal w max. So, maximum width of any term cannot be this is another constraint. So, that is put it cannot be more than the w max, some max value may be put. So, definitely it cannot be more than the total term width. So, that is one type of w max, and also the designer may say, or the designer or the equipment testing equipment may put a restriction on the number of such lines. So, there may be some restriction like this, that wj less or equal w max, that may be put into the system. So, the term design and test scheduling problem is given like this. Given the set of the test set parameters for the course and the total term width w. So, this for every core we know what is the test time for that, what are, so if you put different wrappers, then what are the corresponding test times. Okay. So, it is not a single test time. So, the test set parameters we mean that we want to we know that for each core what is the test time if different term widths are assigned to it. So, different wrapper designs are done with that. So, we assign part of w to each core. So, that is basically designing for every core we are giving some term to it, and design a wrapper for each core. So, we also have to design the wrapper and determine the test schedule such that w is not exceeded any time, and test time is minimized. So, that is the goal, the test time has to be minimized. So, this formulation is a very generic formulation. So, it does not tell whether you are going for this partitioning of the term width or the fixed partitioning or flexible partitioning, nothing. It just says that okay, I have to assign some term width to every core. So, whether that is exclusive to that core or not, it does not tell anything like that. So, if we look into different variants of the problem, so we will see that it is giving us different types, it will give us a different formulation. So, that way it is going to give us different solutions for the problem under different constraints. So, if we are telling that okay, I will do a fixed width partitioning, then that will be that will make it fixed width, and then if we go for say flexible width, then this again the W will be some part of W is assigned to individual cores, but that is more flexible. So, that can be done. So, anyway, so this way the test time has to be minimized, and this test time minimization is one of the constraint. The other constraint that we can have is basically that power limit constraint, that is at any point of time the total power consumption of the system should not exceed the power budget for the chip, and also we can have some total energy limit, like the total this energy with the time into power. So, if you sum them up, so you get the total energy. So, that energy has to be minimized, so that this battery life can be extended and all that. So, there are many variants of this problem, but essentially this is the basic problem. So, we have this TAM design and the test scheduling. So, these are the two problems, and these two problems are solved together to get this test schedule for the SOC.